Hello, in this video we're going to go over some of the properties of integrals. Last time we talked about how to find integrals and the Archimedes-Riemann theorem that allowed us to show some function is integrable and also find the integral as the limit of the upper sum of the sequence that is Archimedean. Okay, so the first theorem that we're going to prove is called additivity. So let me first draw a diagram for this and tell you what that means, and then we will go over the proof of the theorem. So if you look at the graph of a function from a to b and assume that this function is integrable, integral of f from a to b gives you the area underneath the graph of this function, if this is y equals f of x. And if you take some point c between a and b, then you can say the area from a to b is going to be the area from a to c plus the area from c to b. And that is what we call additivity. Okay, so the statement is if f is integrable over ab, then f is integrable on ac and also on a cb, and integral from a to b of f is the same as integral from a to c of f plus integral from c to b of f. So we know that f is integrable from a to b. So what we're going to do is we're going to take a sequence that is Archimedean, a sequence of partitions that is Archimedean over AB, and then we're going to break it up into two different pieces. One gives you an Archimedean sequence of partitions for AC, the other gives you an Archimedean sequence of partitions over CB. However, in order to be able to do that, I would need to have C as one point inside that partition, inside the sequence of partitions. If this point C is not in any of the partitions in that sequence, then we simply add it to the sequence. We simply add it to each of the partitions in the sequence, and that gives us a refinement of the partitions. And when you look at the refinement, if a sequence of partitions is Archimedean, any refinement would also be Archimedean. So that's the idea. We will write down the proof now. So since f is integrable on AB by the Archimedes-Riemann theorem, there is a sequence, there is an Archimedean sequence of partitions, let's call it Pn, of AB for f. Now we are going to take each of these terms of the sequence and we're going to add C to that. So let Qn be Pn union with C. By the refinement lemma, if I look at the upper sum of Qn, upper sum of f with respect to Qn, minus the lower sum of f with respect to Qn, first of all, this is greater than or equal to 0. Second of all, upper sum becomes smaller when you refine it, when you refine the partition, and lower sum becomes larger. So therefore, because of the negative sign, I have this inequality. Now, since Pn is Archimedean, limit of the upper sum minus lower sum for Pn is 0. So the right hand side, this side, goes to 0. So therefore, by the comparison lemma, limit of upper sum for Qn minus lower sum for Qn as n approaches infinity is 0. Therefore, Qn is an Archimedean sequence of partitions for f on AB. Okay, so if you look at Qn, let's say we know that Qn has C. We are going to take the part of Qn that is from A to C. So suppose Qn is x0, x1, there's a C somewhere, and then there is, maybe I'm going to call the term right before C xk, then C, then xk plus 1, and then eventually let's say xm, something like that. Now, if you consider the sequence of partitions Rn, that is Qn intersection with AC, and perhaps Sn Qn intersection with CB. If you look at the upper sum for Rn, that is equal to, it is the sum of mi, I equals 1 to k, times xi minus xi minus 1, because Rn is exactly this from here to here. This is Rn, and this portion is Sn. So if you look at these are the supremums. Mi's are supremums from over xi minus 1 to xi plus a times c minus xk, where mi is the supremum of f of x when x is inside xi minus 1, comma xi, and a is the supremum of f of x when x is from xk to c. So we see that the upper sum for Rn is a portion of the upper sum for Qn. And if you write down the upper sum for Sn, you get, the first one is supremum over this one. So let's call that b times xk plus 1 minus c, where b is supremum of f of x when x is in the interval c to xk plus 1, plus the sum of mi xi minus xi minus 1. This time I goes from k plus 1 to m. So that gives you the upper sum for S, where we have this, and mi is the same thing that we had above. In other words, the upper sum for Pn, for I believe Qn, yeah, upper sum for Qn is the upper sum for Rn plus the upper sum for Sn. So that means upper sum for Qn is exactly upper sum for Rn plus upper sum for Sn. Because again, upper sum for Rn gives you the first portion of the sum, upper sum for Sn gives you the second portion of the sum. And then similarly, lower sum for Qn is just the lower sum for Rn plus lower sum for Sn. Now, what we are trying to show is that f is integrable over a comma c, which means I'm looking for an Archimedean sequence of partitions of a comma c. Rn is a sequence of partitions of a comma c. So if you look at the upper sum of Rn minus the lower sum of Rn, this is going to be First of all, greater than or equal to 0. And this is less than or equal to, if you take the difference of these two, it is the difference of these two plus the difference of these two. So that's less than or equal to upper sum of f with respect to Qn minus upper sum with respect to Rn. Because this guy is that plus something that is non-negative. And since upper sum for Qn minus lower sum for Qn approaches 0, by the comparison lemma, limit of upper sum of f with respect to Rn minus lower sum with respect to Rn is also 0. Therefore, f is integrable. And Rn is an Archimedean sequence of partition for AC, for f on AC. Okay, so f is integrable over a comma c. And then an identical argument shows that similarly Sn is an Archimedean sequence of partitions for f on CB. Okay, if you look at the upper sum of f with respect to Qn, we know that's the same as upper sum of f with respect to Rn plus upper sum of f with respect to Sn. We know that. Now, since Qn is an Archimedean sequence of partitions for f on AB, we can take the limit, and that gives us the left side becomes integral from a to b of f. The right side becomes integral from a to c of f plus integral from c to b of f. And that's exactly what we wanted to show. So just to review, what we did was we took a sequence of partitions that was Archimedean from a to b. We broke it up. First we added c. We broke it up into two parts. The first part is an Archimedean sequence of partitions for AC. The second part is an Archimedean sequence of partitions for CB. And then, since the upper sums add up, when you take the limit, you get the integral from a to b is the same as integral from a to c plus integral from c to b. Okay. The converse of this is also true. In other words, if a function is integrable from a to c and integrable from c to b, then it would be also integrable from a to b. But that's something that is in fact an exercise. You can work on that on your own. Okay. Great. Next, we are going to talk about monotonicity of integrals. So what does monotonicity mean? And how do we prove that? If f and g are functions from a, b to r that are bounded, and f of x is always less than or equal to g of x, we want to show that the lower integral of f is always less than or equal to lower integral of g. So I have an inequality. I can take lower integral from both sides, and I can take upper integral from both sides. And therefore, if the functions are both integrable, then it would be taking integral of both sides of an inequality. What does that mean? What's the interpretation of that, and why do we expect this to be true? We expect this to be true because if you take two functions, what's the integral of the first one? If you say g is always greater than f, integral of the first one, integral of f, is area underneath the graph of this f. Integral of g is the area underneath the graph of g. So you expect that to be larger, clearly. So that's why we expect this to be true. And in fact, not only it is true for integrable functions, it is also true for functions that may not be integrable. So you only need the function to be bounded. Then you can take lower integral or upper integral of both sides. So that's what we're going to do now. Okay, in order to be able to compare these, we would need to compare, first start from a sequence of, first start from a partition and then compare the supremum and infimum. So let P equals x naught, x1, xn, and mi be the supremum of f of x such that x is in xi minus 1 comma xi. Okay, now since I have two functions, I can't really use mi. I would like to use something that indicates which function this applies to. So I'm going to use m sub I and then parentheses f. Similarly, mi of g is defined. So it's the supremum of this set, except that f of x is going to be replaced by g of x. Now, we know this. We know that f of x is less than or equal to g of x. Now, mi of g is greater than or equal to this for every x inside xi minus 1 comma xi. What does this mean? Thus, mi of g is an upper bound for this set f of x when x is in xi minus 1 comma xi. So mi of g is an upper bound for this set. Mi of f is the supremum. Therefore, mi of f must be smaller. Mi of f is less than or equal to mi of g. Now, multiply both sides by xi minus 1. We get mi of f xi minus 1 is less than or equal to mi of g xi minus 1. Add them up, you get the sum mi of f xi minus 1 is less than or equal to the sum mi of g xi minus 1. And that's from 1 to n. Okay, so now the left side is the upper sum for f of the partition P. The right side is the upper sum for g with respect to the partition P. So we went from f of x less than or equal to g of x to being able to compare the upper sums. Upper sums, if you look at upper sums, infimum of upper sums is going to give me the upper integrals. So since upper integral of f, upper integral is the infimum of all of the upper sums. So upper integral of f is less than or equal to the upper sum of f. We have upper integral for f is less than or equal to the upper sum for g. Because this is less than upper sum of g, and this is also greater than or equal to the upper integral. So we have this inequality. So this means this is a fixed number. So the upper integral for f is a lower bound for the set. If I look at all of the upper sums of g, upper integral of f is a lower bound for that. So this is a partition of AB. However, upper integral of g is the infimum of this set. This is a lower bound, so by definition of upper integral of g is the infimum of this set. Upper integral of f is a lower bound. Infimum is the largest lower bound. So that means this is greater than or equal to the upper integral of f. And that's exactly what we wanted to show. So we showed that if f of x is less than or equal to g of x, then upper integral of f is less than or equal to upper integral of g. So we proved this one. This was proof. Now we can prove the other one in a very similar fashion. So I won't go over the proof of that one, but the proof would be similar. Okay. Let's now look at the next theorem. So what does the theorem tell us, and how do we prove that? This is about linearity of integrals. So if you have integral from a to b of alpha f plus beta g, that's equal to alpha integral of f plus beta integral of g. So we need to prove two things. First, alpha f plus beta g is integrable, and second, the integral is going to be additive. In order to prove this one, we can prove two separate things. First, we can prove the additivity, and then we can prove the scalar multiples come out. So we need to prove two things. So first, I'm going to prove alpha f plus beta g is integrable. So how do we prove that? We prove two things. First, if f is integrable and alpha is a real number, then so is alpha f. And when I say integrable, I'm talking about integrability over interval a, b. So maybe I will make that more clear. So if f is integrable on a, b, and alpha is in R, then so is alpha f. And integral from a to b of alpha f is going to be alpha integral from a to b of f. And then second, if f and g are integrable on AB, then so is f plus g, and integral from a to b of f plus g is equal to integral from a to b of f plus integral from a to b of g. If we prove these two things, then we can first break up the plus sign. We can write it down as, you can write down integral of alpha f plus alpha beta g as integral of alpha f plus integral of beta g, and then apply the apply the scalar multiple. Take out the alpha from the first one, take out the beta from the second one. So that helps us with the proof. It makes it less complicated. Okay, so first proof of 1. Some of this is going to be I'm gonna leave it to you to work the details out, but I will give you the main ideas of the proof. Okay, so first I will have to take an interval. I will have to take a partition, look at the supremum, infimum. Supremum minus infimum should be small. So that's what I need to do. Okay. However, if you look at the supremum of, so let me start with this. So let P equals x0 through xn be a partition of AB, and define mi of f mi of alpha f, lowercase mi of f, and lowercase mi of alpha f as usual. So this is the standard notation that we have been using. Capital Mi gives you the supremum over the ith interval. Lowercase mi gives you the infimum over the ith interval. In order to be able to understand these, we need to understand the relation between supremum of alpha f and supremum of f, and infimum of alpha f and infimum of f. Those four things need to be related. So I need to relate these two with these two. And this is an exercise. It's not very difficult to see, but I'm gonna skip the proof of that one. So we claim that, first of all, if alpha is 0, that's pretty clear. So we can just take the case when alpha is 0 out. Because if alpha is 0, then alpha f is just 0, which is integrable, and of course its integral is 0. So the claim is this: mi of alpha f is alpha mi of f if alpha is positive, alpha lowercase mi of f if alpha is negative. So this is something, this is an exercise of supremum infimum. Now, given this, suppose alpha is positive. Suppose alpha is positive. If you look at capital Mi, and also similar for infimum. And if you look at Mi of alpha f, we get alpha Mi of f if alpha is positive, and alpha capital Mi of f if alpha is negative. If you look at the alpha that is positive, then we can look at the upper sum minus lower sum and see what happens. So if you look at upper sum of alpha f minus the lower sum of alpha f, we get the sum mi of alpha f minus lowercase mi of alpha f times xi minus xi minus 1, I equals 1 to n. Since alpha is positive, you can rewrite this as alpha times mi of f minus lowercase mi of f, I equals 1 to n, times xi minus xi minus 1. So this means upper sum of alpha fp minus lower sum of alpha fp is equal to alpha times upper sum of fp minus lower sum of fp. So if you take a sequence of partitions that is Archimedean for f, so suppose Pn is an Archimedean sequence of partitions for f on AB. Then if you take the limit of upper sum Pn minus lower sum Pn, we get alpha times the limit of upper sum for Pn minus lower sum for Pn, which is clearly 0 because it's alpha times 0. So that's 0. Thus, Pn is an Archimedean sequence of partitions for alpha f on AB. And that means alpha f is in fact integrable. Now, if you look at the integral of alpha f, note that the upper sum of alpha f Pn is, if you look at what we did, because the alpha comes out, we get alpha times upper sum of f. We get alpha times upper sum of f with respect to Pn, which means limit of the upper sums for alpha f is equal to alpha times the limit of upper sums of f with respect to Pn. If you look at the left side is the integral from a to b of alpha f. If you look at the right side, that's alpha times integral from a to b of f. And that's exactly what we wanted to prove. Okay, so that's the case where alpha is positive. It's similar when alpha is negative. If alpha is negative, then if you look at the upper sum of alpha f p, you get the sum supremum of alpha f p equals 1 to n, which is, so because alpha is negative, you can take the alpha out, but it becomes infimum. It becomes lowercase mi. Sorry, this is going to be xi minus xi minus 1. Because alpha is negative, we can take out the alpha, but then it becomes lowercase mi of f xi minus xi minus 1. Take out the alpha, we get alpha lowercase of lower sum for f. So then similar thing happens. So if you take the upper sum for alpha f minus the lower sum for alpha f for the sequence that we had, it would be alpha lower sum minus the upper sum. Now the limit of the upper sum minus the lower sum becomes alpha times the limit as n goes to infinity of lower sum minus the upper sum. But Pn is Archimedean, so this one would be 0. And thus Pn is an Archimedean sequence of partitions for f on the interval from a to b. And then if you take the limit of these upper sums, that would be alpha limit of the lower sum. We just proved that here. This is what I'm using. Upper sum of alpha f is alpha lower sum of f. So this is the limit of lower sums of f. The left side is the integral from a to b of alpha f. The right side is alpha integral from a to b of f. So that proves not only alpha f is integrable, but also integral of alpha f is alpha integral of f. Okay, so let's look at the next part. The next part, in the next part, we will have to show that alpha f plus g is integrable. If f and g are integrable, then f plus g is integrable. So we will have to compare again the supremum of f and supremum of g with supremum of f plus g. So if you look at sum x inside xi comma xi minus 1 comma xi, f plus g of x is f of x plus g of x, which is less than or equal to mi of f plus mi of g. That means this is an upper bound. So mi of f plus mi of g is an upper bound for this set of f plus g of x where x is in the interval xi minus 1 comma xi. So the supremum of this set is capital Mi of f plus g. So that's less than or equal to Mi of f plus Mi of g. Okay, so we're almost there. Multiply both sides by xi minus 1 and then add them up. You get the sum I equals 1 to n Mi of f plus g times xi minus 1 is less than or equal to the sum I equals 1 to n Mi of f xi minus 1 plus Mi of g xi minus 1. The left side is the upper sum of f plus g. The right side is the upper sum of f plus upper sum of g. So we have this equality. Similarly, if you look at the lower sums, lower sum would be the other way around. It would be greater than or equal to the lower sum of f, comma g, comma p plus the lower sum of g. So that means if you, so let's just stick to these and then now look at the Archimedean sequence of partitions. So now take a sequence of partitions that is Archimedean for f. So now let Pn be an Archimedean sequence of partitions. So let's just take two sequences of partitions. So let Pn Qn be Archimedean sequence of partitions for f and g on AB. If you take a refinement of two Archimedean sequences of partitions, then you get another Archimedean sequence of partitions. So set Rn to be the refinement of both of these. So the union of Pn and Qn. By what we showed before, we have done this one before, that if you refine a sequence of partitions, then it becomes also Archimedean. So we know that Rn is an Archimedean sequence of partitions for both f and g. So this is not difficult to see, and we have actually done this before. Okay, so now if you take this sequence, we can apply what we have up here. So if you look at upper sum of f plus g relative to Rn minus the lower sum of f plus g with respect to Rn, that becomes less than or equal to. Upper sum is less than or equal to the sum of upper sums. So g with respect to Rn. Lower sum is greater than or equal to. We have done this before. Lower sum is greater than or equal to. So because of the negative sign, I can do that as also less than or equal to, because there is a negative sign. Now, I can rewrite this as upper for f minus lower for f plus upper for g minus lower for g, lower sum for g. Since Rn let me rewrite that. Since Rn is an Archimedean sequence of partitions, limit of both of these, upper minus lower for f and upper minus lower for g is 0. Both of these two are 0. So by comparison lemma, upper minus lower for f plus g, limit as n approaches infinity, upper sum for f plus g minus lower sum for f plus g is also 0. If you look at this inequality, this guy is non-negative and is less than this plus that, both of which are going to 0. Therefore, by comparison lemma, upper minus lower for f plus g must also approach 0. Thus, f plus g is integrable, and integral from a to b of f plus g is equal to limit as n goes to infinity of upper sum for Rn, and is also equal to the limit as n approaches infinity of lower sum for f plus g relative to the sequence Rn. Now let's prove that in fact this would have to be the sum of the integrals. If you look at the upper sum of f plus g relative to Rn, we showed that this is less than or equal to the sum of the two upper sums. Take the limit. The left side becomes integral from a to b of f plus g. The right side becomes integral from a to b of f plus integral from a to b of g. Do the same thing for the other inequality. The lower sum is greater than or equal to the sum of the two lower sums. Take the limit again, and you would get left side becomes integral from a to b of f plus g, and right side becomes integral from a to b of f plus integral from a to b of g. So these two inequalities tell us that integral from a to b of f plus g is equal to integral from a to b of f plus integral from a to b of g. And that's the end of the proof. So that proves that integral is linear. Okay, so combining these two. Okay, so this is a long proof, but it really, like, a lot of it is based on the ideas of supremum infimum. It's a combination of understanding supremum infimum and the Archimedean sequence of partitions. Okay, so now that we are done with this, we are going to look at a corollary of that, which is if you take a function f, then its absolute value is integrable, and absolute value of integral is less than or equal to integral of absolute value. So first, what's the intuition behind this, and then how do we prove that? If you look at the function f, let's say the areas are a and b. Absolute value of integral from a to b would be b, which is the area that is above the x-axis, minus a. So that's the area, that's the integral of f. But if you look at the absolute value, integral of that would be the sum of b and a. So of course the absolute value of integral would be less than or equal to integral of absolute value. But before I can even do that, I would have to know that in fact absolute value of f is integrable, because if it is not integrable, then I cannot just simply talk about integral of absolute value of f. So this needs a little bit of work. So let's go ahead and do that. What I want to do is I want to again relate supremum of absolute value of f and infimum of absolute value of f with infimum and supremum of f itself. So let's take the difference between the supremum and infimum of absolute value and then see what happens. So let x and y be inside the interval AB. So I'm going to look at the difference between f of x and f of y in absolute value. First of all, if I take that is less than or equal to absolute value of f of x minus f of y. This is by the triangle inequality. Well, sometimes we call this a reverse triangle inequality. Okay, now if you look at this, if you look at the right hand side, this would be equal to f of x minus f of y, or f of y minus f of x, which would be less than or equal to the supremum minus infimum, where m. Okay, so and I would like to actually use this one for every interval. So let me start with taking x and y not only inside AB but inside a smaller interval. So xi minus 1 comma xi. So I'm going to call that mi, and I'm going to call this one mi of f minus lowercase mi of f. Okay, so if you look at what we got is that absolute value of f of x minus absolute value of f of y is less than or equal to supremum of f minus infimum of f. Now I can drop the absolute value, because if I drop the absolute value, I get something even smaller. So I would get absolute value of f of x minus absolute value of f of y is less than or equal to capital Mi minus lowercase mi, which means absolute value of f of x is less than or equal to absolute value of f of y. Let me write it down here. Absolute value of f of y plus supremum minus infimum. But these are supremum minus infimum for f and not absolute value of f. Now, this is true for all x and y inside xi minus 1 comma xi. If you fix this one and let x to range over the entire interval, then supremum of absolute value, which is mi of absolute value of f, would be less than or equal to absolute value of f of y plus mi of f minus lowercase mi of f. Okay, so this holds, and that means if I take isolate f of y, I would get lowercase capital F mi of absolute value minus mi of f plus lowercase mi of f less than or equal to absolute value of f of y. And that means, since this holds for every y, then infimum of absolute value would be more than the left side. So mi of absolute value of f minus mi of f plus lowercase mi of f is less than or equal to mi of absolute value of f, which means mi of absolute value of f minus lowercase mi of f is less than or equal to capital Mi of f, and this is absolute value, minus Mi of f. Multiply both sides by xi minus 1 and add them up. So you would get upper sum for absolute value minus lower sum for absolute value is going to be less than or equal to upper sum for f minus lower sum for f. and this is greater than or equal to 0. So similar strategy again. If Pn is an Archimedean sequence of partitions for F on AB, then limit of, by comparison lemma, limit of upper for absolute value of F minus lower for absolute value of F is also 0 as n approaches infinity. And that means absolute value of F is in fact integrable. Okay, so if F is integrable, then absolute value of F is also integrable. Now let's see what we need to prove. So in order to prove the inequality, absolute value of integral from a to b of f less than or equal to integral from a to b of absolute value of f. This is true if and only if integral from a to b of f is between integral absolute value of f from a to b and negative that. Negative integral from a to b of absolute value of f. Now, we can prove this one by monotonicity. So note that f of x is less than or equal to absolute value of f of x, greater than or equal to negative absolute value of f of x for all x. By monotonicity, integral from a to b of negative absolute value of f is less than or equal to integral from a to b of f less than or equal to integral from a to b of absolute value of f. Now we're going to use linearity. That becomes negative absolute integral from a to b of absolute value of f less than or equal to integral from a to b of f less than or equal to integral from a to b of absolute value of f. And that means integral from a to b of f in absolute value is less than or equal to integral from a to b of absolute value of f. And that's the end of the proof here. Okay, so this brings me to the end of this video. So today we talked about linearity, and that was the main thing that we proved, and additivity as well. So we talked about some properties of integrals. We talked about monotonicity, additivity, and linearity. And linearity is really the most difficult of the three properties. Okay, so I will see you in the next video.